So today we're going to be looking at columns. In terms of the theory, it starts off with the assumption that our column, which is going to be loaded at the top, perfectly vertical, it's going to be, because it's a slender column, it's going to bend. And we have this assumption that the two ends are pinned. So that means they can rotate. So it's a bit like having a bolt, and it can rotate freely. So you got a load. When it's applied, the load that it fails at is called the critical load. So we've got it'll buckle at PCR. And then you'll find that in order to sort of use this in design next year, you need to consider the different ways that this column can be fixed at either end, because we don't really have columns where they're all pinned. They're actually, if it's reinforced concrete, it's fixed straight into the ground, so it's a fixed joint. And we can use the Euler formula to work out the critical load depending on the type of end fixings. So have you got this formula written down in your notes? Maybe not. No. If you haven't, then write it down. So what we have is our critical load equals pi squared times by, and it's the two stiffness factors that stop deflection. So it's our A value and our I, and then it's divided by L squared. Now make a note that this L is the effective length. Okay, so write L effective. So when we look at deflection of beams, deflection of columns, again, the two main things that we're looking at is the modulus of elasticity, E, and then we've got here, I is the least moment of inertia, or second moment of area. And when it's talking about the least moment of inertia, if you've got a column, if it's square, it could buckle either way. If it's thinner one side, like the breadth or the depth, then it'll, if you think of your ruler, it will always flex about the thin side. That's your least value of your moment of inertia. So you've got to make sure that you, when you're looking at your I value, so from a few weeks back, we were looking at the I value for a rectangle, which is I is BD cubed divided by 12. So, in terms of the dimensions of a rectangle, if you make your D the smallest value, then you're going to have the smallest I value, and it'll deform about that axis. We don't bother trying to sort of solve the formula from first principles. There are sort of YouTube videos and books that go into that, so you don't have to do that. If anybody's interested in that, then you can just come and see me within my room, and I'll go through that. But you don't need to know, as far as you're concerned, in the examination. If you look at the back page of the handout, showing the formula sheet that you'll get in the assignment, you get this formula, so you don't have to remember it. There's a few assumptions. So, again, whenever you're approaching an assignment, there will be some mathematical type stuff, but there'll be a little bit about definitions and also assumptions. So in terms of the assumptions for this, we're assuming that it's initially perfectly straight. We're assuming that the load is going right down the middle. Like in reality, that's not the case. Because if you think that you've got a load, like a floor resting on this column, you'll find that that force tends to be slightly to the left. So therefore, it'll always be bending it this way. And things aren't perfectly straight. Like if you design in steel, you're allowed to be out 5 millimeters. If you're in concrete, you're allowed to be out 50 millimeters over a number of stories, and that will always give you like this eccentric load. Eccentric is just off to the side, so there's always a moment. But for this formula, we make the assumption that it's passing right through the middle, that it's perfectly straight, that it's very long compared to its cross-sectional area. So it's got a high slenderness ratio, and the assumptions of the theory of bending hold good. So if you can look up them. So here's an example, which I believe you might have in your handbook. Oh, that was very nice of me putting it there. So determine the critical load. You know, it's got the word Euler there, just so that you know which formula you're going to be using, of a solid aluminium rod. It's a circular rod of diameter 12 millimeters. If it's got a length of 1 meter between pin-ended supports, so either sides between pins. So we're given our A value. We're given, in this case, the formula for a circle for the second moment of area. And you're given the answer, and you've got the length. Again, in the assignment, you'll be given all of the formula for the second moment of area. So if we wanted to try and work out what the critical load was, you just go pick off your formula, and if you just write down the answer there, the two errors that people would tend to do on this is, one, they forget that that's the effective length. So, you know, in this case, the length is L, and when it's between pinned joints, L equals the effective length. So that's 1 meter. And the second thing is put everything into the same units. Now, usually I always put everything into millimeters and newtons. Like civil engineers might work more towards using meters and kilonewtons because we're working with much larger forces. I think, you know, the aerospace people and the mechanical, you're going to be dealing with smaller forces. So it's highly likely that you'll be putting everything into millimeters and newtons. Yeah, so the second moment of area is pi r to the 4 divided by 4. And if you put all of these units in, you know, you've got newtons over millimeter squared, and then for the I, you've got millimeters to the 4, and you've got your L squared, so that means you've got millimeters squared underneath. All of the millimeters are cancelled out, and you end up with your force. And our force is 703 newtons. So, very simple example to introduce us to the Euler formula. As far as I know, you have this image here. The only thing that you might not have in is these values here. What this is saying, we've done an example with the pinned. So it's pinned at either side. Where it's pinned, our effective length equals the actual length. If you had the situation where it's fixed in the bottom and then it's waving around the top, this acts as though it's twice as long as this. So in terms of the length, when you have the situation where it's fixed in the bottom and you apply a load on the top and it can move around, it's acting as though it's twice as long as this one here. So this is where, if you have this scenario, so it's fixed at the bottom and free end at the top, when we have our formula divided by L squared, we'd be doing two times this L if it's this scenario. If it's fixed in the bottom and pinned, then it's this will be the shape that it'll follow, and it's the equivalent of 0.7 if it was pinned either side. And this is like the more common scenario. You know, in terms of a concrete column, it's fixed in the bottom, it can't rotate, and it can't rotate at the top. So you find that this is a stiffened area, so it'll be really this half of the column that it can fail in buckling. So when you have it fixed at either side, it's the equivalent of having half of if it was pinned either side. You have to remember the four scenarios. Now this is like the theory for structural mechanics, and I know I haven't put it in. Like I've got some notes here. Like when you come to do some design next year, you'll see how they take that theory into the design of steel columns or concrete columns, and how they use these factors depending on the type of material that you have. Like steel is usually pinned and sort of fixed at the bottom. Concrete is always fixed either side. So as far as you're concerned, you need to know all of them. You'll be given this. You can find in the texts where they look at the radius of a gyration, this r, and you can pick that off a table for individual material shapes. We don't do that within this module. So when you start seeing the value r, just ignore any examples with that. I think the mechanicals and in the aerospace will be using this more next year. If you wanted to try and work out the radius of gyration, it's a square root of I over A. But again, don't need to know that. It's a useful formula for next year. That's if you see that in any books that you're trying to read at the same time.